I was an undergrad graduating from a physics degree when Fife happened, so I was not in Fife. Then I was a graduate student at the University of Colorado, and I found Bretherton's report, Earth System Science, A Closer View. And I really wanted to get the big, messy version of this, but I could only find the little condensed one easily. I loved this diagram. I used to stare at this saying, what should I do? I really like this. I want to be in part of this. And so when I was a grad student, you know, where would you find observational Earth system science in the early 1990s? So I landed in, Boreas, and actually did a little bit of Fife data analysis thanks to Bob Grossman, or Gross Bob Man, as I've heard him called. So anyway, from my experience, Boreas, I watched. This is like going to a college reunion where only your professors show up. I watched you all learn how to talk to each other, and I kind of took it for granted that you have to talk to each other across these disciplines. So this is what I grew up with, so to speak. And it created a new discipline, but I think it's a very natural discipline, Earth system science. We live here. It should be a discipline, not divided. This led to lots of knowledge, but for me also, I learned what I couldn't do and what we didn't achieve, and that motivated a lot more. I mean, it helped also that the Electra, we were kind of outside the fold, so we're often, I wish I could have done that. And so lots of projects from Boreas on were motivated by Boreas. So a little bit about our experiment, and a little bit about things I've done since, and a tiny bit of preaching at the end. So I was part of Don Lenschau's project, PI from NCAR. We had the Electra, which was based in Saskatoon, so we missed most of the parties. It's a big airplane. People doing eddy covariance and boundary layer work. Al Cooper ran the disjunct flux sampler, which was the coolest sounding instrument you've ever heard. You're in the airplane, this is going on the whole flight. It was kind of like a jazz band that had no rhythm. And somebody didn't like the paper that I wrote, and you never got it published. It was probably one of you who reviewed it, but whatever. We had CO2 measurements, and then we had the German water vapor LiDAR from the DLR group in Oberpfaffenhofen. Fantastic instrument. I'll show some pictures from that. And bugs? What bugs? Yeah. The only bugs we got were on the windshield of the airplane. Probably with little bits of Scott Getz in them. Ooh. So I really didn't have the full experience. So our job was to tie together the north and south study areas, fly the whole transect, and try to upscale the whole thing, which was kind of ridiculously ambitious, especially when we weren't really so plugged in with the ecosystem sciences. But it was a good idea. We got some nice measurements. Also look at boundary layer development over the region. So I show you a little bit of the results. So this is from Steve Onkley sitting over yonder. This is the flux map we put together, and we flew a very long transect, often at 100 meters. 100 meters for 6 hours from Saskatoon up to Churchill, and then the next day you'd get up and go from Churchill back. A lot of the time we'd just go from Saskatoon to the northern study area and back, but we do this transect fairly often at low level. This picture's on my wall. This is a faded picture of fireweed from the Churchill airport. And here's some of the measurements. NDVI in the upper left, carbon dioxide flux on the upper right, latent heat normalized by net radiation, sensible heat normalized by net radiation. And this is along that whole transect from Saskatoon up to Churchill. And one thing you can see, of course, is the carbon flux drops as you go north into the tundra, more negative to the further south. The other thing that I remember Piers pointing out that I learned from this experiment, if you look at this IFC1 data on the lower right, sensible heat flux was really high in the spring. This was like it's a swamp out there, and there's a huge amount of sensible heat flux in the spring. It was like a desert before things really got green and warm. It was green, but it wasn't warm. I still don't think we do that right in models, to be honest. And then this was another thing that Steve found, was that the imbalance was correlated with the lake fraction. I don't know if we have small lakes in models yet. So that's just an aside. We also looked at the boundary layer flux profiles and flux development. A couple of papers here, one from me and one from Christoph Kiemle. This was the the Southern Study Area transect we did, about 100 kilometers long. So we didn't have that short flux filtering problem because we had really long transects right across Candle Lake. And here's a picture of it from Jay Lund's paper. And what we did on this a lot was do a stack. We'd fly 100 meters and then about 0.4 ZI, about 0.8 ZI, and then go above the boundary layer with the LiDAR pointing down to get a 2D view of the atmosphere over the system. These were all the stacks that we flew. We flew a lot of stacks. And got data like this is the boundary layer development, and you can see that spring desert phenomena again. The old photocopy didn't reproduce all that well, but the stars that you can barely see are the spring campaign, and the boundary layer is quite a bit higher typically than in the other campaigns. And this is the flux divergence. And still this confuses a lot of people outside the boundary layer community. What are you talking about, flux divergence? I'm just teaching boundary layer class now, and I say dw prime theta prime bar dz. That's it. And they're like, huh? So you can see the water vapor flux divergence. You're typically you're not exporting water, you're importing dry air as the boundary layer grows. Boundary layer is often drying. Of course, it's warming, negative flux divergence. This would lead to drying and heating in the boundary layer over the course of the day, which the interaction was a little complex, often led to a peak of cloud activity in the middle of the day. So that was fun. That was what I learned in Boreas. And then I also learned these beautiful images of the boundary layer from LiDAR. This is the backscatter flying above, pointing the backscatter LiDAR down, ground return at the bottom. And you see that wonderful, complicated, convective boundary layer structure. And we're flying right over Candle Lake. Where is it? You wouldn't know it was even there. And I chased Ronnie Abasar around with this picture like a pitchfork for years after this, saying, where's the mesoscale flow? Look, it's not there. It's not there. And this is the water vapor field that goes along with that. The instrument's gotten a lot better. You can put it with a Doppler LiDAR now and get the turbulent flux profile as a function of height. It's really cool. This is a roll case. 4-kilometer rolls because of the winds and the water vapor along with that. Rapid growth in the spring. This is one where we caught the boundary layer in the act of rapid boundary layer development in the morning. It was a spatial gradient, but it's the time and space interchanged. Cloud cover. Clouds show up and just makes mayhem of the boundary layer top, throwing things all over the place. And that's a stable case. We didn't fly in the morning too much, but you can see the stable structure, remarkably different. So that was really cool stuff to learn. And then we also studied lake flows over the forest, which Jay Lund wrote about, and I thought she was going to tell you about, but she skipped this paper, so that's okay. This is another marker for me for Boreas. This guy was born a week after the third IFC ended, so whenever I look at my son, I think of how long ago it was since Boreas happened. All right, so future stuff. Not future, but what came after Boreas for me. The experiment motivated a lot of things that I wanted to do more of. And I'll tell you, there's a list of things that I got motivated to do more of. I'll tell you a little bit about the ones on the top of the list. So one thing is, others have said, I think Ameriflux and FluxNet came to, not entirely, but to a large extent from the motivation of these experiments. The other thing I did was come up with another experiment, the Schwamigan Ecosystem Atmosphere Study, which somebody showed this in their upscaling and downscaling, the WLEF tower. Somebody had that in their graphic. And I started this off, another Boreas grad, and we called it cheese like Boreas, and it's in Wisconsin. I don't think it's really leaning. So this is still one of the Ameriflux towers. It's now run by Alcor Desai up at the University of Wisconsin. 450 meters, 3 fluxes, flux profile. The idea was, can we do what the Electra did, but keep it there for years? And then have stand-level towers scattered all around it and try to upscale. So this was a project I out largely motivated by what I felt like I wanted to do in Boreas and couldn't quite get it all together yet from what we had for that experiment, partly because of my understanding. And then the other direction we went is to link CO2 fluxes with CO2 mole fractions with the inversions. These should come together eventually. This is still a struggle. This is still hard. So we put towers up around the mid-continent, which were concentration towers. And I can't tell you how many times people say, hey, are your flux towers still running in the mid-continent? Say, well, no, wait, they weren't flux towers. They should have, you know, the whole story goes from there. And these are concentrations over time, and you see a huge drawdown in concentration over the corn, not over the forest. Huge drawdown in both areas compared to Mauna Loa. And you can actually derive regional annual net CO2 flux from this, and it seems to work well when you compare to corn agriculture inventory. So that's encouraging. I'll skip that detail. So, you know, some other follow-ons, we've done more of the same. We've got tower networks in the Gulf Coast, tower network in Indianapolis, tower network in the shale gas fields. All now trying to link inversions up with these flux understandings. Whoops.
Sorry for the inconvenience.
Sounds like the airlines.
And it's alive again. And I'm almost done, so I'll just zip through. This is the fast forward view.
You got a lot of slot.
I did. I'm not a liar. I was honest. So the next thing we're doing is another airborne campaign. I'm back in the air on a C-130 and a King Air. And we're flying greenhouse gas transport to try to understand transport errors in inversions. The Earth Venture program, which this is part of, I think probably when I saw that opportunity, I said, hey, I can propose something like Boreas. That was kind of the reference in my mind for this sort of an integrated multi-year field campaign. And we've flown, did our first campaign, 25 research flights all over the eastern part of North America, about 300 vertical profiles measuring CO2 methane. Across storms, we're going for the bad weather now. We haven't done the bad weather before. We're doing the nice weather too, but the bad weather is interesting. And so this is an example of a flight across a front. You can see the front, left is the cold sector, right is the warm sector. Big coherent change in CO2 and methane across the cold front. Alan Betts showed you the ECMWF system, which is simulating CO2. And they've got all these beautiful CO2 fields. Do they make any sense or not? We're going to check them out. We've got the data now to try to verify whether or not they're doing the right thing. Same thing for methane. Boundary layer up to top of the upper troposphere. All right, so a couple of reflections and I'll be done. What do we need? Intensives like Boreas or long-term studies? And do we need flux measurements? Do we need concentration measurements? Do we need remote sensing or do we need in situ data? We need them both. But the pendulum that we're in kind of swings back and forth, and you get a lot of this at one time, then a lot of this at another time. And right now, if you're not doing satellite CO2, it's hard to find funding in a lot of ways. Or if you're not doing cities or natural gas. And there's not that much connection, from my perspective, with the climate modeling community at this point. And these are issues. I think we need long-term study areas. I think things like the southern study area and the northern study area or the cheese cluster, I think these are really good ideas because a single point is really hard. Upscaling across complex surfaces needs detailed areas where we study for a long time to take the details apart. So then we can really extrapolate across the planet better. And we need to oversample. We don't know what to measure. We can't measure everything everywhere, but we have to some places measure everything so then we can know how to scale back to do the right job for the longer term. So I think we've got to push the pendulum a little more back the Boreas direction at this point, to be honest. All right, so Boreas and Fife changed us. It certainly changed me. It created a new community, showed us how to do more ambitious and comprehensive science, and very collaborative. It's our job, somewhat, to maintain that community and these capabilities. So let's watch what we're doing, keep it balanced, speak out, and keep up the good work. Thank you.